Hello, my name is Sun Yao Chiu. So in this video, I will present our BMVC paper called KPE, Keypoint Pose Encoding for Transformer-Based Image Generation. So existing transformer-based text-to-image models, the most famous one is the DALL-E. So DALL-E accepts only one single type of modality input, which is the text. So on the other hand, so there are other transformer systems like a VQ gun that is able to do accept pose as a conditions. We show that we can also we are the first to show that we can use both text and pose as inputs to generate image, and the result is actually better than either of them or two of them combined. So let's talk about how we represent pose. So this is how VQ gun or all the transformers generally represent pose. It first use a skeleton image. It breaks them down into a grid of like a smaller patch. Then flatten them because a transformer accepts this flat input, and then they encode each of these is a patch using image encoder into discrete tokens. So what we find that there are two things observed. The first is that there are a lot of redundancy in the background, the background image, the background picture, which do not contain information. And then secondly, this 2D spatial information is lost with this flattening. Because before that, when we use convolution neural network, the convolution kernel have to slide through this skeleton image to capture of this locality, the spatial locality. That is why in the past people have to create skeleton image from the key point, because everything there's no new information apart from the key points. But we needed this structure for this convolution kernel to work. But with transformer, we don't need that anymore. That's why it inspired us to create a new method called Keypoint Pose Encoding (KPE), that we encode the key point directly by passing the skeleton image part, which resulted in 10 times more memory efficient and a lot faster, 73% faster in both inference and in training. Then we also created a new method called people count error. That is a new metrics to detect image error in this people image error. And then the third contribution is, of course, we create the first text and pose to image transformer model, and we show that it outperforms the state-of-the-art DALL-E. So this is our method, this KPE. So we shown that this there's 3 people in this image. Each of them have a set of key points. So in this case, we use open pose scheme, which have 25 key points. So that means we will have a fixed 25 number of tokens. So each token corresponds to a key point of this specific key point of the body part from different people. So this one will be, let's say, the right eye of person 1, people 1, person 2, person 3, etc. So because of this, and then we encode them directly, we do not use any image encoder. So because of this, okay, so we use a fixed key point tokens, number of tokens. So it will be a lot smaller than the VQ guns like 2056. If you assume we use commonly use a 16 by 16 grids of tokens. So it is 10 times smaller. Because of this, we do not need to use big VQ gun model to encode the image, the skeleton. So it will be a lot faster. We don't require additional GPU memory to do the processing, so it's faster, use less memory. And it is also invariant to image domain. That means that if you train this one, if we encode this VQ gun using VQ gun, so this might different from the image domain like natural landscape that is trained on using your VQ gun autoencoder. That means it can create something that looks totally different. If your data set is different, then it can be different. But ours, we only use the key point, which is generic, which is a number. So it doesn't care what your autoencoder is trained on. And also we can scalable to a high resolution. So if we decide to, because all these XY coordinates they are normalized to 0 to 1. So it is invariant to your image size. We do not need to retrain anything if we decide to increase the resolution. So unlike VQ you probably will have to use a higher number of tokens if you increase the resolution, or you have to basically train a separate autoencoder just for these skeleton images. If you were to decide to maintain this one, but then you have to use 2 autoencoders in your system, and which leads to all these problems like more memory and so on. So our method is clearly better because it's invariant to high resolution and image domain. It's fast. This shows how our model works. So if we ignore the part in the pose encoding, so this is the DALI architecture where you have to encode the text into tokens. You encode your the image into tokens. Then the transformer will basically try to predict the same image token from the text tokens. Then we add a pose conditioner here. So this is our pose method. So we encode our pose using KPE into tokens. And then now there are 2 additional. There's one additional condition. Means apart from text, we use the pose. In our experiment later, we actually also do a comparison by replacing our pose method with VQ method. That means it is looks the same like this part, but instead of encoding real images into tokens, we encode these skeleton image into tokens and then put it here. Okay, this is how we do the comparison. So that is for training. For inference, we don't need this part. Okay, this portion is not needed. So we fix this input, the text and the pose, and then we use that to generate the first output, the first image token. Then after that, we move this one, the output in the pupil and the as the input, and then we fix this one, fix everything here, and then run another for pass to try to predict the second image. Oh, by the way, after we run one for pass, we actually we don't take the token with the highest probability. We actually sample with some random probability. We say we take the top 5% of the highest token with high probability, and then we sample randomly. That gives us some randomness in variation in the image. And we, in order to test our whether our Keypoint works for multi-person, we create a multi-person dataset from this DeepFashion. DeepFashion by default, so the DeepFashion they only have a single person in the image. We combine them to create a dataset that contain 1, 2, and 3 people with corresponding text description. So this is the result of our model. So we can see that we can able to in this experiment, our experiment, we can generate up to like 3 people in an image using with different complex pose and different scale. So even your one is bigger, one is smaller, standing further away, we can still able to do that. And we can do partial view. That means if some key points are missing, for example here, this part here, and this part here, we're still able to generate, because we know we have learned the anatomy of the people that they should have legs. So we can do partial view, and it's also very accurate. So in this exam, accurate and also consistent. So we use this guy Keypoint. This is for illustration. We actually use Keypoint as input, and also all the text as an input. And we can see that we set this as an input. It can generate very consistently, the people pose, where they stand, when they stand, how and their pose, we stay true to our pose and also to the text description. So in this case, we use a lady. The one on the left is a lady, and then the one on the right is a man. Okay, so same for this one. Okay. And then next come to our matrix called PCE. So how this works is that ground truth is just true, the expected number. So it comes from text and it comes from the pose information. So in this case example, so this is the images created by the by model, but it of course contain error. So we send this image into open pose. That open pose will detect the key point, and then it group them to a specific person. So all the key point here belong to this person. All the key point here belong to this person. That it detected an additional like arm, because it cannot belong to either these two person, either of these like person. So it allocate this one to the third person, which of course doesn't exist. But because of this discrepancy in this number, then we know, okay, there is an error. So this is a new method to able to detect error in people error in the generated images. So there are more examples here that you can look at. Right, as a result, so we compare against DALL-E, which is text only, and DALL-E and VQ using skeleton pose encoding, and our methods outperform in each of these categories. We have a better image quality, lower, this one especially, so lower error rates, lower error rate in the image. Okay, so this is the conclusion. So this concludes everything. So we have created a KPE, efficient pose method, a representative method. We have created a PCE matrix to detect image error, and we created a state-of-the-art text to people image generating model with post conditioning. Thank you for your time. Bye bye.